Welcome to the final part of Lecture 2 on this course on chemical process design. One of the problems we've highlighted so far is that when dealing with multiphase reactors, it is possible that the overall rate-limiting reaction step may not be the chemical kinetics, but the mass transfer between phases. Sometimes this can be overlooked, leading to designs that don't work. What I would like to do in this part of this lecture is to work through an example of how to estimate whether a gas-liquid reaction is mass transfer limited or not. We'll start by examining the kinetics of a multiphase reaction and, in doing so, remind ourselves of the importance of taking the time to understand the units that the kinetic expressions use. Then, we'll work through the process of estimating a mass transfer coefficient, estimating total mass transfer area due to a bubble swarm, and estimating concentration gradients. We can then compare these estimations to the kinetic requirement. As we work through this example, we'll also see the importance of using dimensional analysis to check equations found in the literature, as well as the importance of reading literature thoroughly. So, let's take a scenario. Let's suppose that you've got some reactions being carried out in a bubbling, agitated batch reactor. So here on the whiteboard is your bubbling, agitated batch reactor, and here also on the whiteboard are some idealised chemical reactions. This is actually an abstracted version of a real system. The real system involves the synthesis of a herbicide, and the kinetics are somewhat complex, but this simplified version serves to illustrate the point that I want to make. Let's suppose that we've got our herbicide precursor A, and we're oxygenating it. And that produces our herbicide component B plus formaldehyde plus carbon dioxide. Let's suppose there's a side reaction as well, that formaldehyde is further oxidized to formic acid. So there we have our two reactions. It takes place in a multi-phase system. Rather than using pure oxygen, we're going down an inherently safer route of using air as our reaction medium. Now, let's suppose that we've gone and talked to our friendly chemist and that we've got some reaction kinetics for these two reactions, which is great. So, the next thing we need to do is to understand the units that these reaction kinetics are written in. So, when you've got reaction kinetics, whether from a discussion with a chemist or from the literature, sit down and examine them and make sure you understand how things are being measured. It sounds like a statement of the obvious, but as we'll see from this example, sometimes the reaction units that are convenient from an experimental standpoint from a chemist require a little bit of interpretation by the engineer. So let's take that first reaction. So we've got our rate constant K1, we've got a concentration of A, which is in moles per litre. We've got a concentration of oxygen, which is the partial pressure of oxygen in pounds per square inch, and the overall rate of the reaction is in moles per litre per minute. Okay, there's nothing terrible there. It's not SI, but at least we've got moles and we've got moles per litre. We need to be careful that we use minutes and not seconds, and we've got to be careful of our partial pressure units, that they're being used as one of the old imperial units as pounds per square inch rather than Pascal. So there's a little bit of conversion required for that first kinetic reaction, but it's not too dreadful. Let's look carefully now at the formaldehyde oxidation reaction. So the overall reaction units are milligrams of formaldehyde consumed per litre of pure water, not solution, pure water, per minute. We've got an oxygen concentration term now, and that is now the dissolved oxygen concentration in a liquid phase in moles per litre. It's not the partial pressure in pounds per square inch, as was in the first equation. It's in a dissolved oxygen phase in moles per litre. And you've got your concentration of formaldehyde now in mass terms in milligrams per litre. So you can go and look at this reference and you can go and see the full reaction, and you'll see that these are the units that are used. So this is a real world example, and this is the sort of thing that the chemical engineer has to deal with. As we've said, the first equation is okay. We've just got to be careful of those imperial units of the partial pressure, pounds per square inch. The second equation needs careful thought, since we need dissolved gas concentrations. So let's think about that multiphase mass transfer. Let's think about dissolved gas concentrations, and let's think what it is we're trying to achieve. So here on the whiteboard I've put a schematic diagram of an oxygen bubble, and if we look at the oxygen interface, If we specifically focus on the liquid side of that interface, we can see that at the gas interface we've got some kind of interface concentration. We might have a stagnant film, and then we've got a bulk liquid concentration of oxygen. And so that gives us our mass transfer driving force for that mass transfer process. So we need to be able to estimate these parameters to get a quantitative measure of what our mass transfer rate actually is. So let's think about how we would write down our mass transfer rate. Let's say our rate of interphase mass transfer is going to be measured in moles per cubic metre per second, so it's in volumetric terms. That's going to be equal to a mass transfer coefficient KL. We need a mass transfer area, and note from the units here what we're using is a volumetric area, so we're looking at the total metres squared per cubic metre. Then we've got our concentration driving force measured in moles per cubic metre. So that would give us our rate of mass transfer of oxygen, and what we're aiming to do is to compare that oxygen mass transfer rate from gas to liquid to the rate of kinetic consumption of oxygen from the kinetic equations that we've got. If our kinetic equations require less oxygen than is being transferred by mass transfer, then we're kinetically limited. If, however, our kinetics require more oxygen than we're able to transfer in our multi-phase system, then we're mass transfer limited. Note that we're also in a batch reaction, and so the concentration of reactants and the chemical rate is going to change over time. So we may well find that we might start off mass transfer limited and end kinetically limited as our batch time goes from start to finish. So be aware that we may need to switch regime at some point. Okay, so what we need to do is to find a method of estimating KL, our mass transfer coefficient, a means of estimating the volumetric surface area of bubbles, which we'll do by our two-phase flow knowledge, and then a means of estimating the oxygen concentration that is dissolved in the liquid phase, which we can do by vapor-liquid equilibrium considerations. So let's start at the beginning. Let's think about KL, and I would advise you thoroughly to go and look at the literature. A lot of mass transfer work has been done. There are a lot of established relationships that you can find that you will be able to use. What you might find is that your mass transfer coefficient depends on the nature of the bubbles that you've got. And here's some examples of useful mass transfer relationships. If you've got bubbles that are under 2.5 millimeters in diameter, the equation that I've put on the whiteboard will apply to them. If your bubbles are over 2.5 millimeters in diameter, then you've got a slightly different mass transfer relationship, and both of those relationships come from that paper that I've referenced on the whiteboard by Calderbank and Mu Young. So if we look at these mass transfer equations, let's see what's in them. We've got some groups that look kind of like Schmidt numbers, we've got some gravity terms, we've got some terms that involve density, but we've also got terms that involve diffusion coefficient. So if we look more carefully, the diffusion coefficient is of the gas in the continuous phase. So the continuous phase in these bubbly systems is going to be the liquid phase. So what we want is the liquid phase diffusion coefficient, in this case of oxygen. So these mass transfer relationships are easy to compute as long as you know the physical properties of the materials that you're dealing with, and can also get a decent estimate of this diffusion coefficient. So again, let's dive back into the literature, and in a paper by Sridhar and Potter you can find that there is an expression that gives you the diffusion coefficient of oxygen in the liquid phase, and it's phrased in terms of critical properties. So again, if we look at the equation very carefully, we'll find that we've got the critical molar volume of oxygen featuring, the critical molar volume of water featuring, and I've put the numerical values of both of those on the board for you, and then you've got Avogadro's number, universal gas constant, temperature, and continuous phase viscosity measured in Pascal second. So be careful with your units, make sure you understand your constants, make sure that the units of the diffusion coefficient that's calculated here are the units that you need to use in the mass transfer relationships. There's nothing here that is too complicated though, so it should be relatively straightforward to estimate what our value of KL is. So that's one of the three things that we need to know to work out our overall mass transfer rate. Okay, let's now proceed, assuming that we know what KL is, and let's go to that third point. Let's look at the vapor-liquid equilibrium between oxygen and water. Now, we could think about doing this in a number of different ways. We could do this from first principles. We could find an appropriate activity coefficient model or an equation of state and solve it. You might end up having to use something like UNIQUAC or NRTL, but don't reinvent the wheel. There are many things that already have these activity coefficient models, these equations of state built into them, with numerical solvers to give you an answer, and also with all the parameters that the equations need to be solved for a particular chemical species. So think about your process simulator. Within Unisim or within HISIS or DWSim or Aspen, you will find that UNIQUAC and NRTL are already implemented. They already have data banks with all the material parameters that these equations need, and you can get predictions of your vapor-liquid equilibria over a range of temperature and pressure. However, don't forget previous discussions you have hopefully had about the importance of making sure that any thermodynamic model is appropriately validated. Just assuming something applies and just making calculations with it doesn't actually validate it. If you haven't got experimental data or literature data against which to compare those predictions, how can you trust those predictions are correct? So, look to the literature. Somebody might have already done the experimental and theoretical work for you, and this is the case for oxygen. And if you look in the literature, you find a very nice correlation such as this. You've got your dissolved oxygen concentration as a function of density, pressure and temperature. Brilliant. Look carefully whenever you get equations from the literature, and I want to illustrate this point here. So here on the whiteboard now is that equation that I just put up. Now let's look at the units very carefully. Let's look at the left hand side to start with. There you have your equilibrium concentration of oxygen, moles per cubic metre. Let's now look at the right hand side. You've got a group of terms that are dimensionless in curly brackets. That's stated in the paper. So then let's look at the left hand side and right hand side dimensions. On the left hand side you've got that C star, that concentration, moles per cubic metre. On the right hand side you've got the product of a density and a pressure. Atmospheres, kilos per cubic metre. There's a dimensional inconsistency here, isn't there? So always check your relationships to start with. Never assume that what's written in a piece of literature is correct. So if you dig deeper into the paper, you find something else. On page 7 of the paper, you find the equation that appears in the abstract with an additional term in it, an exponential term that was missed out in the abstract. It's very, very easy to do. If anybody has written scientific papers, they'll realise just how easy it is to make typographic mistakes, and if anybody's reviewed them, sometimes it can be very hard to spot those mistakes being made. So never assume that things are correct, always cross-check. So here on page 7 we have the correct version of the equation with that exponential term operating on that dimensionless group. So what we now have to resolve is this dimensionless conundrum, or this dimensionality conundrum that we still have. The dimensions of the left hand side and the right hand side still aren't the same. So what do? Go and check it using a different means. Look at the ranges of applicability at the correlation first. This particular correlation is valid between 273 Kelvin and 616 Kelvin, which is brilliant, a nice wide range, and between 1 atmosphere and 60 atmospheres, again brilliant, a nice wide range. So what you would do, get your process simulator, cross-check it against an appropriate activity coefficient model. Let's take UNIQUAC, and let's look at the numerical values that UNIQUAC predicts against what the numerical values that this correlation predicts. And if you sit down and do that, you'll find they're essentially the same. So this is good. So there is a dimensional inconsistency. So there's something going on there that's a little bit odd, but the absolute numerical values that this equation gives are correct, or at least are consistent with the numerical values that you might obtain through using an equation, an activity coefficient approach such as UNIQUAC. So always persuade yourself that what you are using has some form of correctness. Try and imagine that you are convincing a sceptical colleague that the data that you are using is correct. How are you going to do that? That should be the way that you're convincing yourself. So just don't take things at face value. Go and validate, And if you can't quite resolve that validation, go and then cross-check. So we've now got a means of estimating that concentration of dissolved oxygen in water. We've had to do this with care. We've taken literature data, we've carefully checked that literature data against another means, in this case prediction using an activity coefficient model. So now the final piece of the puzzle to get our calculation of KL is a means of estimating the volumetric surface area of this particular bubble swarm. So this is where your two-phase flow knowledge comes in. You know that if you've got a given bubble diameter, you can work out its non-dimensional bubble diameter and the rise velocity of a single bubble in an infinite medium via something like Wallace's correlation. We know then that the rise velocity of a single bubble in an infinite medium is going to be different to that to a bubble swarm. The rise velocity of the bubble swarm is going to be slower, but we can estimate what that rise velocity is using something like the Richardson and Zaki correlation. That will also yield the bubble void fraction alpha. And so then we can start to say, right, we know what our bubble swarm rise velocity is, we know what our void fraction is. We can then find out what our flooding void fraction is and avoid having that kinder downfall problem in our piece of process equipment. We can also use our bubble void fraction, of course, along with the number of bubbles to figure out our total bubble surface area. So that gives us the final piece of the jigsaw. We've got KL, we've got now our volumetric surface area of bubbles via our knowledge of two-phase flow. And we've also now got a semi-validated way of figuring out the dissolved oxygen concentration in water. Therefore, we can work out KL over a variety of different concentration ranges. We can compare that against the kinetics requirement for oxygen that we've got from our rate equations. And we can figure out whether we're mass transfer limited, kinetically limited, or whether we swap between a mass transfer limitation and a kinetic limitation during the course of the batch reaction. So let's summarise a few key points. Remember that when you look at the literature for kinetic data, it's largely written by chemists, and they will have used units that are convenient experimentally for them. So you will have to think carefully about what these units mean and about how you calculate the rates based on those units. And as we've seen in this example, you might have to do quite a bit of digging to find out things like oxygen concentrations or dissolved gas concentrations. A really important point is always make sure that you have checked correlations in the literature. Use dimensional analysis first to make sure there isn't an inadvertent typo, and then if any inconsistencies remain, go and find a way of cross-checking the numerical data that is yielded by them. And we did that in this example by employing our process simulator and by looking at the Uniquac activity coefficient model's prediction of the oxygen concentration in the dissolved phase. There is a lot of data in the literature on mass transfer. Use it. Don't reinvent the wheel, but use it with your eyes open and use it carefully. And pay attention to your two-phase flow lectures. They're really, really important when it comes to the design of multi-phase reactor systems.